Welcome to Chapter 2. So we will be starting off with sections 2.1, 2.2, and 2.3, which for the sake of a kind of better flow to all of this new information, we're combining the sections all together in the notes here because there are things we might be jumping around a little bit from section to section, but all three of these sections will be covered through this set of notes. In Chapter 2, we are introducing the concept of linear algebra. In these first sections in particular, we're going to start talking about the concept of a matrix and matrices and how we're going to be using those to solve problems using linear algebra that we will encounter all throughout this chapter. So we're going to be looking at definitions and notation, how to perform algebra with matrices, and introducing terminology for systems of equations. So to start us off, we start with the familiar, the concept of a linear equation. So a linear equation is an equation that has the following form. So a1x1 plus a2x2, etc., all the way up to an xn equals b, with x sub I being unknowns, and a sub I being given constants, and b being a given constant as well. A collection of linear equations is called a linear system. So when we think of a linear equation, like in our algebra class, we think of y equals mx plus b. And that is the slope-intercept form of a line. But when we talk about linear equations, we're really just talking about equations of multiple variables where each variable has a power no greater than 1. So you can have linear equations that have many different variables in them, not just x and y. And linear systems take those linear equations and put them all up with each other. So like, for example, this right here would be a linear system because you've got three separate linear equations all in conjunction with one another. When it comes to solving linear systems, if we want to find, like in this case, all of the values of x, y, z, and w that would satisfy all three of these equations simultaneously. If a linear system has at least one solution, then we call that system consistent. Otherwise, if it does not have at least one solution, then we call it inconsistent. Now, if we want to solve linear systems like this, the most effective way to do so is using matrices. Okay, and so this is where we're going to be spending most of our time throughout linear algebra, especially in this chapter, focusing on matrices and how we can use them to solve linear systems of equations. So, an m by n matrix is an array of numbers arranged in m rows and n columns. So consider the system from above. So this one right here. If we wanted to create a matrix for this system, we'll call it A. We're going to create some brackets here. Each of the values is going to represent a different column in the matrix, and each equation is its own separate row in the matrix. Now, we don't bring the variables with us, we only take the coefficients. So we're going to have -3, 2, 1, -1. The second one, there's 2x, so we want to line this up. So the 2x goes under the -3 there. There are no y's in the second equation, so that's a 0. There's 2 z's and no w's. And then the last one, there's no x's, a -1y, a 5z, and a 2w. So this is arranged in m rows and n columns. So this matrix would be a 3x4 matrix. So it's got 3 rows, 4 columns, right? So 1, 2, 3 rows, and then 1, 2, 3, 4 columns. This matrix here, because we're only working with the coefficients, it is appropriately named the matrix of coefficients. Now, we didn't include all of the b values, those constants on the right-hand side of the equations. We can create a separate matrix for those, and the notation that we use, we're going to have A, and then it looks like a little pound sign or a number sign or a hashtag sign, if you like, up above the A in the superscript up there. So this gives us -3, 2, 1, -1. So we'll keep this all the same. 2, 0, 2, 0, 0, -1, 5, 2. And now we're going to draw a vertical line here, a bar, separating off these. This kind of takes the place of the equal signs here. And then on the right-hand side, we have the 5, 3, and 0 from up here in the equation. And then we close off the matrix on the right of those. So notice this one now is a 3x5 matrix. This notation, this symbol that we use, and the label of this matrix as a whole, this is called an augmented matrix. Okay, so augmented. So like it's been like adjusted slightly or added on to, because that's exactly what we've done. We've included this augmented column over here. This is our augmentation bar that goes right here between those. We have our augmented column over here, and this symbol, this number sign up here, indicates that it's an augmented matrix. All right. Notationally speaking, if we want to talk about any one of the components within the matrix, we can use notation like this. So the entry in row I and column J is denoted A sub ij. So like for example, in A above, A32, that's the component that's in the third row and the second column. So that's this one right here. So that would be -1. A24, so that's second row, fourth column. So that's going to be 0 right there. Okay, and we can do this for every component within the matrix if we wanted to, right? This is A11, A12, A13, 14, A21, 22, 23, 24, A31, 32, 33, 3, and 3, 4 at the end there. So every component can get its own label, and that's how we'll identify which specific component we're talking about if we're trying to single one out. Now, when working with matrices, there are a lot of different things we can do with them, including some algebra and some calculus, and some operations that are not as familiar to us because they're unique to matrices. So the first one is the transpose of a matrix. So if we want to transpose a matrix, that means we're going to be interchanging the rows and columns of the matrix. So the first row becomes the first column, right? And then the second row becomes the second column, and vice versa. So it turns an M by N matrix into an N by M matrix. And the notation we use for this, it's denoted A to the T, it looks like. Okay, now it's not an actual power, it's just a notation. But consider the matrix A from the previous example. Trying to fit all of this on here. So this matrix right here, if we're going to construct the transpose, so this was a 3 by 4 matrix. Now it's going to be a 4 by 3 matrix. So you can either go row to column, or column to row, either way. So we can start with the first row. First row becomes first column. So that's going to be -3, 2, 1, -1. Second row becomes second column. So 2, 0, 2, 0. Third row becomes third column. 0, -1, 5, 2. And now we come back in here, and we see the matrix that we have created. This is a 4 by 3 matrix. All right, 4 rows, 3 columns. That is the transpose of the original matrix A that we had on the previous page. You can also encounter matrices that have functions inside of their components. So we don't have to limit ourselves to only numerical values. So for example, you have the matrix B, which is e to the 2t, negative sine t, 3, and ln of t. So this is B as a function of t. We can perform operations on these matrices as well, including differentiation and integration. So if we wanted to take like B prime of t, for example, we would just need to take the derivative of each individual component. So that would be 2e to the 2t, negative cosine of t, 0, and 1 over t. Or on the other hand, if we wanted the integral of b of t with respect to t, we would similarly integrate each component. We would get 1/2 e to the 2t, and each component would need to get its own c value, its own arbitrary constant. So I'll call them c1, 2, 3, and 4. So we're going to get cosine of t plus c2. We're going to get 3t plus c3. And integral of ln of t, it's a little bit of a trickier one. That's t ln of t minus t plus c4. Okay. So we can also perform calculus operations on matrices if so desired. Now, a lot of what we're going to be doing, especially at first here, is we're going to be manipulating the matrices algebraically. So we have the concept of addition, subtraction, multiplication, and scalar multiplication. The concept of division does not work within matrices, and we'll talk more about that as the chapter progresses. But in terms of addition and subtraction, given two matrices A and B of the same size, we can compute A plus B and A minus B slot by slot. So that's a very important thing, that we can go slot by slot or component by component. So we just add corresponding components to each other. So that's going to be the 1 and 7 together give us 8. 2 and 8 give us 10. 3 and 9 give us 12. 4 and 0 is 4. 5 and 1 is 6. 6 and 2 is 8. So this would be our new matrix found by taking A plus B in this case. We can also perform scalar multiplication. Scalar multiplication, so we take k times A for a scalar k. you scale each entry of A by k. So in other words, this common multiple here gets distributed to every single component within the matrix. So this is going to become 2, 4, 6, 8, 10, 12. So that's scalar multiplication. Now, multiplication, matrix multiplication itself, is a little bit trickier. It's not quite as simple as matrix addition, subtraction, and scalar multiplication. Especially in the sense for addition and subtraction, they have to be the same size. Matrices that we're going to multiply cannot always be the same size. There are cases where they can be, but a lot of times they won't be. So given an M by N matrix A and an N by P matrix B, we can form an M by P matrix A times B. So the way this is going to work, so if, like for this matrix here, this one is a 2 by 3. This one is a 3 by 4. So the only way we can multiply matrices together is if the middle component matches. So again, in this case, a 2 by 3 and a 3 by 4. These two have to match in order for the multiplication to work successfully. And if it does match, the new matrix that we result in is going to essentially get rid of this component, and it will be a 2 by 4. So that's what all of this is saying. So we have a 2 by 3 times a 3 by 4. When we do the multiplication, the 3's essentially kind of balance each other out, if you will, and we're left with a 2 by 4 matrix. And that's going to be the matrix AB. Now, how do we get the components of AB for matrix multiplication? Because these are not the same size. So what we have to do is we have to multiply a row by a column to obtain a component. So like for this matrix, we're going to have, AB 1, 1. We're going to have the 1, 2, the 1, 3, the 1, 4. We'll have AB 2, 1, 2, 2, 2, 3, and 2, 4. Those will be all the components that we need. If we want the 1, 1 component, we're going to multiply the first row with the first column. So first row of the first matrix, first column of the second matrix. So what that looks like, if you remember from Calculus 3, the concept of like a dot product, it's very similar in construction to that. So our 1, 1 component, basically you're going to go row to column, multiplying the corresponding pieces and adding together. So we're going to take 1 times negative 1, so this times this, plus second times second, so 2 times 2, plus third times third, so 3 times negative 1. So that's going to be negative 1 plus 4 minus 3. So 4 minus 4, which is 0. So the 1, 1 component is 0. Now if you want to move over to the 1, 2, you go first row, second column. So we go 1 times 0 plus 2 times 1 plus 3 times 3. Okay, so that's, again, AB 1, 2. And go 1 times 0 plus 2 times 1 plus 3 times 3. And that gives us 2 and 9 is 11. You want the 1, 3, you go first row, third column. And that's going to give us 2 plus 2 plus 0, so 4. And then we go first row, fourth column. So we get 1, 0, and 3. So 1 plus 0 plus 3 is 4. and that's our first row. For the second row, now we go second row, first column, second row, second column, second row, third column, second row, fourth column. So we do that for all 4 of those components. So we get -4 plus 10 minus 6. And that's going to be also a 0. We go here to here. That's 0, 5, and 18. So that's 23. Here to here, we get 8, 5, and 0. So that's 13. And here to here, we get 4, 0, and 6. So that's 10. So that's going to be our 2x4 matrix AB, okay, found using matrix multiplication. So matrix multiplication, it takes a little more time to kind of get down the pattern of it, get into the habit of it. But once you get it down, it all goes fairly quickly. Now, for the next few properties that we're going to talk about, we have to assume that A is a special type of matrix. We say that A is a square matrix. A square matrix is one whose dimensions are the same. So it has the same number of rows and the same number of columns. Like with these ones, these were not square matrices, right? 2x3 and 3x4. But if we have a case like this one down here, this is a square matrix, right? 3x3, right? 2x2, 4x4, whatever the case is. So if A transpose is equal to A, so if a matrix is equal to its own transpose, we call A symmetric. In other words, Aij equals Aji. Okay, so if you look, A11, 22, 33, those are all the same, but the 1, 2 position and the 2, 1 position are the same. The 1, 3 and the 3, 1, the 2, 3 and the 3, 2, right? Everything is the same. Which means that if you transposed it and you turned the first row into the first column, notice there would be no change. Like if you interchange these or flip these around, there would be no change. So if the matrix is equal to its own transpose, that's going to be a symmetric matrix. If A transpose is equal to the opposite of A, then we call A skew symmetric. So Aij equals negative Aji. So like with this one, A, we have 0, 3, negative 2. And this one, 0, negative 3, 2. So the transpose is exactly the opposite of the original. Negative 3, 0, 5, 3, 0, negative 5. 2, negative 5, 0, negative 2, positive 5, 0. So by transposing the matrix, you have created its exact opposite, and that is what makes a matrix skew symmetric. So a lot of terminology coming at us here in these sections. The entries that all have the same row and column along a square matrix, so the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, etc., those components of a square matrix comprise what we call the main diagonal. So the main diagonal is all those components basically that just run straight across the middle of the matrix diagonally. Okay, so like down here, that would be these. Okay, so it's all the ones 1, 1, 2, 2, 3, 3 that run right down that middle there. The sum of the terms on the main diagonal of a square matrix is called the trace of A. denoted TR of A. So if we were to add up all of those components, that's the trace of the matrix. Couple of other types of special matrices. An upper triangular matrix has all entries southwest of the main diagonal are 0. So southwest, so southwest is over here. So if we look at this example here, so here's our main diagonal. All entries southwest, so down and to the left, all of those entries are zeros. Okay, this is why we call this upper triangular, because all of the other entries are up here. So kind of in that upper triangle is where all the non-zero entries are. Now, for one like this, notice that there is a 0 on the main diagonal, and that's perfectly fine. The only condition of an upper triangular matrix is that the component must be 0 if I is greater than j. So like second row, first column, this component has to be 0. But first row, first column, those components are equal to each other. There's no restriction that says it can't be 0. So this one also is still upper triangular. Okay, so there can be zeros in the main diagonal, and it will still be upper triangular. It's just the only condition is that the ones below the main diagonal have to be 0 in order for it to be upper triangular. Similarly, a lower triangular matrix has all entries northeast of the main diagonal are 0. So, like in this example, here's the main diagonal. Everything above it, so northeast up here, is 0. So all of our other terms are down here, hence the lower triangular name for this type of matrix. Okay, so in other words, if the column number is bigger than the row number, then that means that the term is 0. Right, over here, first row, second column, right? First row, third column, etc., etc. Same condition applies. Terms on the main diagonal may be 0. That does not break any restrictions of this type of matrix. Now, the way that we use matrices to solve linear systems is by establishing linear systems in terms of these matrices. So we do what we did earlier. So we take a system of linear equations and we basically strip it of all of those coefficients and the constants on the right-hand side. We form this augmented matrix here. So we've got the first equation, right, the A11, 1, 2, 1n all the way through. And then the second one, the third one, fourth one, fifth one, etc. We take those, put them into the matrix here, and then we can solve this instead of solving this. The solution sets will be the same, and we'll look at how to solve it more completely in the upcoming sections. So we can write the linear system in another way. So this is the same thing as this, just written slightly differently. Notice if you were to actually perform matrix multiplication on these two matrices, we would go row times column equals first component, right? The first row, first column is 1, 1. So we would get A11 x1 plus A12 x2, A11 x1 plus A12 x2, all the way to A1n xn. That's this one, equals the 1, 1 component, which is B1. Okay. And then, of course, same thing if you did the second row, first column equal the 1, 2 component, or excuse me, 2, 1 component. Okay, so this is the same as this, just put into this condensed form here. that'll make it easier for us to solve in the upcoming sections. The notation we use for this typically will have A, which is an m by n, times the vector x, which is an n by 1. So oftentimes these one-dimensional matrices like this get labeled as vectors because it's just a single row or column of components. That equals the vector b, which is an m by 1 matrix. The shorthand that we use for this is ax equals b. So when you see an expression like this being written, that is just the same thing as a system of linear equations set up in this condensed matrix form. So finding any solutions to this will be the same as finding solutions to this, which will be the x1, x2, x3, all the way up to x sub n. Okay, so again, that's our goal here in this chapter, is being able to solve these linear systems using matrices. Now, before we get to go on to do that, we have a few other special matrices that we have to look at and a few properties that we have to talk about. So the first one is the m by n matrix of all zeros. This is called, appropriately, the zero matrix. So the zero matrix, which is denoted 0 sub m by n, or 0 sub n, or just 0, and we just note the context is appropriate when writing it in that notation. And so the zero matrix is just a matrix of all zeros. Another very important matrix, the n by n, so it's a square matrix with ones on the main diagonal and zeros elsewhere. This is called the identity matrix, written I sub n or just I. The identity matrix, with all ones on the main diagonal, zeros everywhere else, that matrix is important because it is essentially the multiplicative identity. And what I mean by that is it kind of acts like 1 when you're multiplying matrices together. If you multiply any matrix by the identity matrix, you end up getting the original matrix you started with. So zero matrix is what we would call the additive identity, because any matrix plus 0 is itself. And this is the multiplicative identity because any matrix times this one is itself. So, and that's outlined here in these properties as well. So assume that A, B, and C are matrices of appropriate size. A plus the zero matrix equals A. Okay, so that's what I meant by additive identity. Anything plus the zero matrix is itself. Anything times 0 is the zero matrix. Okay, so if I take a matrix, multiply it by the number 0, the 0 would distribute to every component within A, and it would create a matrix of all zeros. If we take AB times C, that's the same thing as A times BC. So the order that you perform those multiplication operations in does not necessarily matter. You can multiply A times B first, or you can multiply B times C first, and then multiply the other. Matrix multiplication is distributive. You can distribute across addition and subtraction. The only thing you have to be careful of is that matrix multiplication does not go the other way. So whatever side it started on, it has to conclude on that same side. So if A is on the left here, it has to be on the left in both of these. Same thing with this, A plus B times C. You can distribute it, just make sure that the C stays on the right-hand side. If you take a matrix times the identity, that's equal to the matrix you started with. and that works both from the right-hand side and from the left-hand side. So no matter how you multiply by the identity, a matrix will just be itself. If you take the transpose of a transpose, you get back the original matrix, right? Because if you transpose it once, you flip the rows and columns. And if you transpose it back, you've flipped the rows and columns back. The transpose, interestingly enough, because it looks like a power, but it's not a power, the transpose of a sum A plus B is actually the sum of the individual transposes. So the transpose can distribute across addition. And the other one where it gets a little weird, the transpose of A times B is not equal to them individually. It's actually B transpose times A transpose. So the transpose acts a little weird. It acts a little differently than you would maybe expect it to, but this is how it works. And you can try this out. There are ways you can prove this as well, and you can just even try out examples to verify it to yourself that this is in fact the case. But an important note, like I was just mentioning up top, it is usually true that A times B is not equal to B times A. Now, we don't put this as a property up here because it's not always true. There are some cases where A times B equals B times A, but most of the time it is not the case, which is why the order of matrix multiplication matters so much. So because if we take these matrices, for example, so this one is a 2 by 3. This one is a 3 by 2. If we multiply them to get the matrix AB, so it's going to be a 2 by 2. So we take this row, this column, so that's 2 plus 9 plus 20. So that's 31. First row, second column, we get 4, 12, and 24. So that's going to be 40. Next one, second row, first column, 0, 3, and 10. So that's 13. Second row, second column, 0, 4, and 12. So that's 16. If we were to switch these around and do B times A, now we're doing the 3 by 2 first and then the 2 by 3. So by switching these. So now the matching component in the middle is the 2's. So the result is going to be a 3 by 3. So already we can see that it's not going to be the same. But if we go through this process, so we do first row, first column. So that's 2 and 0. That's 2. We do first row, second column. So that's 3 and 2 is 5. First row, third column is 4 and 4 is 8. And et cetera, et cetera. So if you do the rest of this, you get 6, 13, 20, 10, 21, and 32. Very clearly not the same matrix. As a result, this is why matrix multiplication, we have to be very careful with it, okay? Because not only is it a little bit trickier to make the computation, but the order in which you multiply them very much matters. And if their sizes don't match up, you can't multiply them at all. It just so happened that these two could be multiplied either direction, but they did not produce the same thing. Now, a note that follows this, if you wanted to square a binomial like this, a plus b, it doesn't exactly work the same as in algebra with algebraic expressions. So it doesn't equal a squared plus 2ab plus b squared, and that's precisely because of this definition here. So if we took a plus b squared, that's the same thing as a plus b times a plus b. We can perform like that foiling operation on it, so the first, outer, inner, last. So we do first is a times a, so that's a squared. Outer is a times b, so that's plus ab. Plus the inner. Now, this is where it gets tricky. B times A, B comes first. B is before A, so that's BA. And then last is B squared. AB and BA are not equal to each other. Okay, that's the property we just talked about up here, which means that you can't just switch the order and combine them to make 2AB. And that's the core of this property, is that we cannot combine AB with BA because they're not necessarily the same thing. And again, in general, they won't be. All right. But that brings us to the end of sections 2.1, 2, and 3. So again, this cumulated section that we have here. So this has been our introduction into the concept of matrices, looking at special matrices, looking at operations we perform on matrices, relating it back to systems of linear equations. When we come back in the next section, we're going to start looking at how we can solve systems using matrices, how we're going to perform operations on them and simplify them and use them to actually start solving equations and solving problems. And that's coming up throughout the rest of this chapter.